Hello, today's lesson will be on intermolecular forces, which are the forces that hold atoms and molecules together. So polarity is the first thing that we have to look at. The polarity of two different atoms is going to help us figure out what kind of force is held between each atom. So when atoms share valence electrons, they do not always share them equally. Frequently, one atom has a stronger attraction for the electrons than the other atom does. This uneven attraction causes the electrons to be held closer to one end of the bond than the other. We say this makes one end of the bond slightly positive and the other end slightly negative. A covalent bond with uneven sharing of electrons is called a polar covalent bond. A bond in which the electrons are shared is called a nonpolar covalent bond. Electronegativity is a measure of the ability of an element to attract electrons to itself. Put another way, electronegativity is the measure of the force of attraction that exists between an atom and a shared pair of electrons in a covalent bond. Linus Pauling developed a scale of electronegativities that run from a low of 0.7 for several metals in group 1 to a high of 4.0 in fluorine. We'll be using the numbers that Linnaeus found to help us determine the polarity of different compounds. Sometimes it's difficult to decide exactly what we consider nonpolar, polar, or ionic, since bonds may have some covalent characters and some ionic characters. For convenience, for beginning students, we have established some arbitrary guidelines. So if the difference of the electronegativities, so if you take the larger electronegativity and subtract the smaller electronegativity for each of the atoms, if it's between 0 and 0.49, you have a nonpolar covalent intermolecular bond. If it's between 0.5 and 1.69, you have a polar covalent intramolecular bond. And if it's bigger than 1.7, you have an ionic bond. We're going to work through some examples. So, when I look on the periodic table, I find that nitrogen has an electronegativity of 4.1. and hydrogen has an electronegativity of 2.1. So when I subtract 2.1 from 4, I end up with a difference of 0.9. If I look on my table, I find that for a difference of 0.9, I end up with a polar covalent bond. For MgO, magnesium oxide, I look and I find my two electronegativities are 3.5 and 1.3. When I subtract, I get a difference of 2.3, which is greater than 1.7, so I find I have an ionic bond. For chlorine 2, I have 2 atoms of chlorine, so I'm going to subtract the same electronegativity from itself because the electronegativity doesn't change, it's the same atom, and I end up with a difference of 0. Therefore, I have a nonpolar molecule. For HCl, we have a difference of 0.9, which puts us into the polar covalent bond type. And finally, for H2O, we have a difference of 1.4, which makes it a polar molecule. So we just looked at intramolecular forces, which were the forces between molecules in one specific compound. Now we're going to look at intermolecular forces, which are forces between molecules outside of themselves. So there's a few different forces that we're going to look at. Van der Waals are intermolecular forces. That is, they are attractions between neutral molecules. There are dipole-dipole interactions and hydrogen bonds, which hold polar molecules to other polar molecules and are the strongest van der Waals forces. Then we have London dispersion forces, which hold nonpolar molecules to other nonpolar molecules and are the weaker type of van der Waals forces. Dipoles. So polar molecules or dipoles are molecules that do not have an even distribution of electrical charge. These attractions between polar molecules are called dipole-dipole interactions. Hydrogen bonds are special kinds of dipole-dipole interactions where the partially positive end of the molecule contains a hydrogen atom. Dipole-dipole interactions and hydrogen bonds are the strongest types of van der Waals forces. The weak attractions between nonpolar molecules are called London dispersion forces, and they are the weakest of the van der Waals. An instantaneous dipole is formed when electrons moving from in the molecule get off-balanced for an instant. So, for that instant, one end of the molecule is positive and the other end is negative. This will cause charges in the neighboring molecules to set up a whole chain of reactions, of short-lived attractions. So, just as we could figure out intramolecular forces from within one molecule, we are also able to figure out intermolecular forces between multiple molecules. So if the difference of electronegativity is 0 to 0.9, you have a nonpolar covalent intramolecular force, and it's also a London dispersion force. If you have a 0.5 to a 1.69, you will get a polar covalent molecule, and a polar covalent molecule will either be attracted to other molecules by hydrogen bonds, it's only if there's a hydrogen in the molecule, or a dipole-dipole when when it's a molecule that doesn't have any hydrogen in it. If your difference is 1.7 or higher, you're going to have an ionic intermolecular force. You'll also have an ionic intermolecular force, where the positive ions are attracted to the negative ions. So we're going to go through some examples to find the intramolecular forces, so the nonpolar covalent, polar covalent, or ionic. We're also going to do these same examples for intermolecular forces in the next few slides. So I just went through and I figured out the differences of all of the molecules, and then we're just going to use the table to figure out what kind of intramolecular force we're dealing with. So CH4 methane has a nonpolar covalent bond because the difference of its electronegativities was 0.4. CF4 had a difference of 1.5, therefore it's a polar covalent molecule. HI had a difference of 0.6, so that should be a polar covalent molecule. I don't know why it says something different. CO2 has a difference of 1, which makes it a polar covalent molecule. NH3 has a difference of 0.9, which also makes it a polar covalent molecule. And NaCl has a difference of 2.1, which makes it an ionic molecule. So to determine the intermolecular forces, so whether it's a London force, dipole-dipole, hydrogen bonding, or ionic, we use the same values that we determined before. So CH4 has a different electronegativity difference of 0.4, so therefore it is a London dispersion force between multiple molecules. CF4 has a difference of 1.5. Because there's no hydrogen in there, that makes it a dipole-dipole. HI, again, it says 0.6, so to my understanding, this should be a hydrogen bond because there is a hydrogen molecule within the molecule there. CO2 has an electronegativity difference of 1, which makes it a dipole-dipole because it does not have any hydrogen. NH3 has an electronegativity difference of 0.9, which makes it a hydrogen bond because of the hydrogen within the molecule. And finally, NaCl has a difference of 2.1, which makes it an ionic bond because it's greater than the 1.7. Another bond type that we'll look at is metallic bond. So metallic bond forms between multiple metal atoms. A metallic bond is formed by the mutual attraction for each other's loosely held valence electrons. Metals can be thought of as positive ions, the nucleus and the inner shell of electrons, all of the atoms except the valence electrons. is in a sea of loose valence electrons, or delocalized electrons. A mixture of metals is called an alloy. So, a few more examples looking at whether a substance is metallic, ionic, or covalent. So we're going to look at the numbers, the differences in their electronegativities. If what we're given is only 1, we can't find the difference of the electronegativity, but you should know on your periodic table where the metals fall. If you don't, come see me and we'll figure it out. But anything that falls within the metals on your periodic table is obviously going to be a metallic bond. So RbCl is ionic. Cl2 is covalent. Au, which is found within the metals on the periodic table, is obviously a metallic. BrO3- is covalent. Mg3N2 is ionic. Pt is metallic. Al is metallic. And Ag is metallic. The final type of compound that we look at in this course is called a network covalent solid. In this type of bond, atoms share valence electrons by the atoms, but the atoms are arranged in a regular crystalline pattern in which each atom is covalently bonded to its neighbor in all directions. Therefore, you do not have a collection of small molecules that are easily separated from each other, but the whole system is one giant molecule held together by this network of strong covalent bonds. Network solids are extremely hard and brittle and do not conduct electricity. The exception is graphite, which will conduct electricity. They are also insoluble in common solvents. Diamonds are a form of pure carbon. Carbonundrum is a solid carbide. Quartz is silicon dioxide. And these are all examples of network covalence solids. So therefore, if you have a diamond, basically what you're looking at is one molecule. It's not a bunch of separate ones, one big molecule, which I think is kind of cool. So that's the end of today's lesson. I hope you enjoyed it, and I hope you filled in your notes. If you need to go back and look at anything to get them filled in, please feel free, and we'll see you tomorrow in class.